Hi, everyone. Welcome to our 96th session of the MedAI Group Exchange sessions. This week, we have Julia Wolleb from the University of Basel here with us to speak about all their work on denoising diffusion models in medical imaging. Julia is a postdoc in the Center of Medical Image Analysis and Navigation at the University of Basel. She holds a PhD in biomedical engineering and a master's in mathematics from the same university. Her research mainly focuses on the automatic detection of pathological regions in medical images, and she's interested in the development of robust and reliable deep learning methods for medical image analysis in clinical applications. And she has explored various aspects of deep learning, including segmentation, weakly supervised anomaly detection, image to image translation, and domain adaptations. So, thanks so much, Julia, for joining us today. And before we start, do you have any preferences on how you'd like to take questions? Do you prefer them all at the end, or is it okay to interrupt you?
So for me, it's perfectly fine if you just interrupt me anytime with any question.
Awesome. Okay, perfect. So I guess let's try to make this session as interactive as possible. And without further ado, let me hand it over to Julia.
Okay, great. Thanks a lot. Well, thanks a lot for this invitation. I'm very excited to present our work here. So as I said, just interrupt me anytime. Also, if there's a problem with the audio or anything, just let me know. Okay, so today I will talk about denoising diffusion models because that's some research that's been going on in our group for like 2 years roughly. And so first, I'm not sure how familiar you are with the idea of denoising diffusion models, and that's why I just like quickly introduce them. So the type of models I'm talking about is based on this paper called Denoising Diffusion Probabilistic Models that was published 2020. And then 1 year later in 2021, there was this paper called Diffusion Model Speed Guns on Image Synthesis. So this was just like an improvement of the initial paper, and all the code or all like the framework that we used in our research was based on then this work. So the basic idea is that we have a data set of images, and the goal is to generate new synthetic images that follow the same distribution. So denoising diffusion models are a class of generative models that are designed to generate fake data, basically. So in the beginning, we have a training data set, for example, a data set of fish, and we take just any image of this data set, and this is denoted as x0 because there's no noise on this image. And then the idea is to add small amounts of noise for many, many time steps t. So we start with the first step, 1, and we add a little bit of noise, and we get a slightly noisy image x1. Then we add a little bit of noise again, and then we get a slightly more noisy image x2, and so on and so forth. And if we do this many, many times, we end up with a completely noisy image x capital T. And if you do this for many, like a lot of time steps, this follows a normal distribution. And then, so this is the easy part, this is just adding noise. And then we want to go backwards in this process. So we want to remove noise for many, many time steps t until we get back our initial image of this fish. And this forward noising process is called the noising process Q. And when we remove the noise, that's the denoising process P. And by definition, the noising process Q follows a normal distribution for every single time steps. And there we fix the variance scheme in the beginning. So we know, like, we have a normal distribution with this mean and this variance, like in every single time step. Now the trick is, the denoising process is the thing that is learned by the model. So we train a model that removes noise from images. And because we know that we follow a normal distribution in the forward noising process, we also want to simulate a normal distribution in the denoising process. So we have this p theta is a normal distribution. And actually what we learn is the mean and the variance, so the mu and the sigma of this normal distribution. So we want to train a model that learns to predict the mu and the sigma. That's what we want. So during training, we pick a random time step t in between 1 and capital T, where capital T is a really large number. For example, it can be 1000. And then we add t steps of noise to our input image x0, and then we get a noisy image xt. And then we train a model to predict the noise pattern epsilon theta that needs to be subtracted from xt to go one step back, so to predict a slightly denoised xt minus 1. So our diffusion model follows a unit architecture that takes xt as input, and it predicts the noise pattern epsilon that needs to be subtracted from xt to get the slightly denoised fish xt minus 1. And so the easy explanation is because we know what noise we added, we know what noise we need to subtract, and that's why we can take the MSE loss between the true noise and the predicted noise. A slightly more correct way of saying this is that we have the noising process Q and the denoising process P, and we want that those two distributions match. So we compare them with the Kullback-Leibler divergence, and because we know that they are both normal distributions, we can rewrite this Kullback-Leibler divergence as an MSE loss between the predicted noise and the true noise. So that's how the training of our model works, and the model is just a unit architecture, so this is nothing fancy. And then once we have trained our model, we want to generate synthetic images. And there the idea is that we go through an iterative process. So we start from random noise. So our x capital T is drawn from a normal distribution. And from there, we predict xt minus 1, then xt minus 2, and so on and so forth. So we go through this whole process. And in the end, we reach x0, and this is our synthetic image. And so this is this formula, how this denoising process works. So the U-net, this is the diffusion model, predicts the noise given xt, so the noisy image at time step t. It also takes the time information, and it predicts this noise pattern that needs to be subtracted from xt to get xt minus 1. And here I made a video. So we start from random noise. And in every step, the model predicts the most probable next step. And in the end, we end up with a completely fake chest X-ray image because I trained this diffusion model on a dataset of chest X-ray images. And now, one important thing to note is that we have a random component epsilon here. So epsilon is drawn from a normal distribution. And we add this random component in every time step of our denoising process. So this is a random process. Okay, so far that's for diffusion models. If you have any questions here, just interrupt me because that's the background we deal with for the rest of the presentation.
Just a quick question, sorry, if I may. Have you experimented with other architectures than the U-net?
No, so actually not other architectures. So what we have experimented with is how deep do we need to go in the U-net? So how many downsampling and upsampling blocks do we need? And one thing is that there are attention blocks in the U-net. And the question then is like, how many attention blocks do we need and at what layers? And we have done some experiments with that, but we never changed the U-net like this whole encoder decoder things.
Questions on the epsilon. So it's a single number or the matrix?
Which one?
The epsilon, because you mentioned epsilon theta with respect to time. So it's a number or just a matrix?
The theta, you mean?
Yes. The parameter you are using, you're getting it from
epsilon theta. Theta are the model parameters, actually. So that's the parameter setting of my trained model.
I think the question was if epsilon is a matrix for you, or is it a single scalar number?
No, epsilon is of the same dimension as x. So if x is an image, epsilon theta is also an image. Otherwise, I couldn't do this.
Yeah.
Okay.
Right.
Sorry.
So on the same ground, is this architecture is also true for RGB images, color images, or always the X-ray and MRI, CT scan is always black and white or color?
You can train it on colored images. The only difference then is that XT has 3 channels, so RGB, and then my epsilon also have 3 channels because they need to be of the same dimension. But you can have as many channels as you like.
Got it. Thank you.
Sorry. I just didn't get that. Why don't we just subtract the predicted noise from the input image? And sorry, I didn't get that. Would you please elaborate more that why are you using this formula?
Yeah. Okay. So why we don't just do one step from noise to the image?
Yeah, exactly.
Okay. This goes a bit more into the detail of like the theory. So the idea behind these models is that we, with this diffusion process, we can approximate ordinary differential equation. And this kind of denoising process is a way to solve, like to discretize, like the solution of this equation. And so the way it's written here, it's similar to the Euler solver of the ODE. And there the idea is that the more time steps you take, so the smaller the delta t is, the smaller the time step you take, the more accurate is your solution. But this is a trade-off. So the more steps you take, the better might be your image, but the longer it takes. And there are approaches that try to speed this up, so to like have fewer steps, but this comes at the cost of image quality usually. And here I'm just talking about the basic idea, like the first paper. And there I think they either picked 1,000 steps or 4,000 steps, so quite a lot. And it worked, like the image quality was amazing. And then afterwards, people started to think about how can we make this faster, which would be making fewer steps.
Yeah, thank you.
Actually, one more questions about like image quality measurements. Like you are using MSE. Have you tried any other measurements like SSIM or something else which is applicable, or is the best?
Yeah. Okay. So here we are still talking about image generation, like fake data. And in the papers, they like explored like the threshold inception distance, so FID. They looked at how like the variability among the images that are generated and stuff like that. So the MSC is for the training of the diffusion model. It doesn't say something about image quality. Image quality is something that you need to evaluate like on the sampled images then afterwards. And this was done in these papers that I presented in the beginning. And later on for our applications, like for the medical applications, we do use then different scores, but this will be later on in the presentation. Okay, then thank you for the questions. Then I just move on, and if anything else pops up, just stop me. Okay, so yeah, as I said, so far we just talked about image generation, and this was like diffusion models became very famous due to applications like this. So for example, you have a text prompt like a teddy bear's swimming at the Olympics 400-meter butterfly event. And then the output image is something like this. So really astonishing and surprising results. And these text-to-image models are amongst others Dall-E, image and Stable Diffusion, and so on and so forth. And now the question is, how can we take this new method and apply it to medical applications. And there, so now, today I'm going to talk about work we did in our group, but there are like tons of other papers solving other tasks. So today I will present you one segmentation approach, then related to that contrast harmonization for MR images originating from different scanners, an implant generation, and also weakly supervised anomaly detection. And you just go through these 4 tasks. So I start with the segmentation task. And so this work was presented in the middle conference last year. It's called Diffusion Models for Implicit Image Segmentation Ensembles. And there the idea is that we do have brain MR images. So I took the BRATS data set, and related to the questions before, here we have 4 input channels because we have 4 different MR sequences. And this is my brain MR image B that shows the tumor, and the task is to segment the tumor. So we want to generate the segmentation mask, and for this, we go through this generation, like this iterative image generation of the diffusion models. So we start from random noise, XB capital T, and we go through this whole denoising process. And in any time step T, so now we are here in this time step small t, we want to predict a slightly denoised segmentation mask XB T minus 1. But we want to generate a segmentation mask that corresponds to my brain MR image P. We don't just want any binary segmentation mask. And for this, we need to add this anatomical information. And we do this through concatenation. And so we concatenate channel-wise. So we have 4 channels for the brain MR image and 1 channel for the noisy segmentation mask. And all these 5 channels are then passed through the diffusion model, and the diffusion model predicts the noise pattern. And this noise pattern is then subtracted from XBT to predict a slightly denoised XBT minus 1. And this is done in every single time step. And at some point, we get then XB0 if we do this for all time steps. And this is our predicted segmentation mask. And here in the formula, you can see, so we compute XBT minus the predicted epsilon to get XT minus 1. And we also have a random component, again, in this denoising process. And now this random component can be used to generate an ensemble of segmentation masks. So we have our brain MR image B, and we go through the sampling process of our diffusion models. So we start from a noise pattern number 1, and we go through the denoising process, and we predict the segmentation mask number 1. And now if we draw a slightly different noise pattern 2, and we go through this random process a second time, we get a slightly different segmentation mask. And if we do this n times, we get n slightly different segmentation masks. And then we can consider the mean of these segmentation masks and compare it to the ground truth. And we saw in our paper that this improves the segmentation performance. But what is maybe more interesting is that if we look at the pixel-wise variance over these n segmentations, we get some sort of uncertainty estimation. Like this pixel-wise map shows us the areas where the model is unsure about its own prediction. And this can be used in the clinics as model interpretability and tell the human experts like, hey, check there, I'm not sure. It could also be used as a safety margin for tumor resection. And here are some results. So,
sorry, I have a question.
Sure.
So in your previous slides, when you add the noise, do you add the noise to the original images, or you just start from random noise to
we just start
denoise?
from random noise.
But I thought that's the image segmentation task. You need to segment the organ from the given image, no?
So what happens here is, so we start from random noise, and here in the bottom you see the brain MR image B. So we do add this through concatenation. So we start from random noise, but in every step we concatenate the brain MR image B as just to add or to provide the anatomical information to the model.
I see.
Julia,
So
one more
in
question.
every
Sorry, go ahead.
sorry. So in every step, do you concatenate the original image with the noise, or you concatenate the noise with different images?
So maybe if I go one slide back here. So in every step, I do this. I take the noisy segmentation mask that I have now in my time step T. I concatenate it with B, and then I compute xt minus 1. And then in the next
So what
step,
is B?
B is the brain MR image. So do you see my red, the laser?
Yes, I do
Yes.
see that.
B is the 4 MR sequences of the BRATS dataset. So this is the brain MR image.
So is B the same for every time step?
Yes. Yes.
Okay, that's my question. Yes.
Sorry. Yeah. B,
Okay.
that's the
Great.
same for every time step.
Thank you.
Okay, Julie, on the same line, in the next slide, you mentioned about the ensemble. So, so each time step, like suppose you took one noise and you sample 4 sequences, so that become one model, and like that you go for n models of ensemble. Is that the one?
I'm not quite sure I understand correctly. So
You mentioned about the ensemble model over
Yeah.
here. So what is that architecture over here? Like, I mean, how it become ensemble?
It's called ensemble. So I have one model. It's always the same model. But since I have this random component in this sampling process, so with the same model, I can generate as many segmentation masks as I want, just because it's random.
Okay. So you basically fix the model. Okay. So only
Yeah.
the input noise is changing that creates so many. Yeah. Okay. Sure. Thank you.
I have a question here. So you mentioned that like if you give different noise, then the segmentation will become differently, right? Like in here you show 3 kind of segmentations. So eventually, which one that you choose, or what's the funding of your paper? I don't get that clearly.
So here is an extreme example, because here I chose one where the differences are big. Usually they are not as big, but I think it's a good example to show that I can fix the number of segmentation masks n, and I took it as an odd number, like 5 or 7 or 9. And then I take the mean. So for every pixel, I take the majority vote of my ensemble. So if, for example, I check 1 pixel here and all 5, let's say I have an ensemble of 5, and all 5 segmentation masks tell me, yes, this should be part of the tumor, then of course I choose it as a part of the tumor. But maybe it's, for another pixel, it's 3 versus 2. And then I just took the majority of the predictions to be like, to say that this pixel belongs to the tumor.
Okay, so if I understand correctly, so basically, let's say that we randomly choose 5 type of noise, and we generate the 5 type of segmentations, and then we take the maybe something like a voting technique to decide our final segmentation areas.
Yeah, exactly.
Okay.
So voting in this
you.
sense is, I take the average and threshold it at 0.5. That was the decision, basically.
Okay, got it. Thank you.
Thank you.
So I have a small question. So these 4 images, which is denoted by B, is it that variations of that same image, like different angles? Suppose I take X-ray of an ankle. Sometimes the doctor takes the picture in different angles. So this B means those images or not?
So you mean here the 4 channels? Or I'm not quite sure. So the 4 channels are 4 different MR sequences. So T1, T1 contrast enhanced, T2, and flare.
Right, right. But I got that. But if you imagine, sometimes the doctor says to take in this angle, X-ray, take the X-ray in this angle, or the 2 angles. So what I mean to say that for the same X-ray, you will get 5 or 4 different pictures.
I'm not sure we are talking about the same here. So here we have brain MR images and not X-ray images. And I never cared about angles. Here, so these are perfectly registered and sliced. So we
Okay.
have all slices just like from top to bottom. And regarding the X-rays, like that I used later on, we just use the Chexpert data set.
Lateral view, or there is something like lateral view and
exactly.
full view.
Yeah. So there I just took the frontal. I didn't take both sides.
Okay. Thank you.
Actually, a last question you mentioned about the registration. What kind of registration you used for aligning the structure?
So here I took the Bratz data set, and they are registered by like just the way I downloaded them. They are already pre-processed, so they are sculptured, registered.
Okay. It's already done. Okay, in that case.
All right, one last question. So
Sure.
is it here that you basically try to learn the condition distribution given all these MR images, and you're actually learning the probability distribution of the segmentation? Or you train diffusion model with the original MRI data? That's
No.
I think it's a little bit different.
So I conditioned them already during training. So the denoising process that I tell them on is conditioned on this brain MR image, and not just
I think my question is the diffusion model trained on the original data set, or just trained on the segmentation?
It's trained like in this way. Maybe let me just go one slide back. So it's trained on the segmentation. So it's trained to denoise the segmentation, but conditioned on the brain MR image.
Yeah, that's my question. That makes sense.
Okay.
Thank you.
Okay. So here are just some results. So on the left, you see one sequence of the input, then the ground truth, then, so I go column-wise, sample number 1 and sample number 2. So this is if I go through this process twice, then the mean map and the variance map. So this is my uncertainty map. And here you see, usually it's the boundary of the tumor where the model was unsure. Sometimes in the second row, it's a bit trickier, but still it gives a good uncertainty estimation that can be used by the human experts eventually. Okay, we implemented this method in Monai. So there is the Monai generative that came out earlier this year, and there we implemented some tutorials. And if you're interested how this concatenation and model training works, you can just check out this tutorial. There we did it on a small data set, just 64 by 64, but like the whole mechanism just works exactly the same.
Sorry, I have another question. Like, have you compared this segmentation technique with like the other segmentation technique? Because I feel like if you have to do the ensemble inference during the full denoising process, that would take a very long time.
Yeah.
And whereas compared to some of the embedding where you could just use the prompt and then tell. So have you compared like the differences or?
Yes, so we compared to NNUNet and SegNet and some other net that I don't quite remember. So it's just like the classical segmentation approaches. And what we did, so with the segmentation performance, we are not as good as NNUNet, but you're also not far off. But what we then argued is like, okay, segmentation-wise, NNUNet solves the problem anyways. we were just wanted to show this way of estimating uncertainty using this randomness in the generation process, and thereby then being able to draw as many samples as we want. So as an ensemble of n segmentations, and with this then compute this variance map. That was like the conclusion of the paper, basically then.
Okay, thanks. That makes sense.
Okay, then with this, so if we keep in mind how we trained our diffusion model, so we wanted to have an output which was our segmentation mask, and we conditioned it in every time step on some input, which was our MR image. And you can use the exact same technique for contrast harmonization. And why do we need contrast harmonization? So, for example, if you have two different MR scanners, one is 3 Tesla and the other one is 1.5 Tesla. And if we compare those two images just visually, we already see the differences between the two. And this leads to problems because if we have then downstream tasks that work automatically sometimes with some sort of algorithm, but if we cannot compare those two images from different scanners, then the downstream tasks will also perform worse. And this is a problem in clinical applications. So what we try to do is that if we have a source contrast S, for example, if you have a 3 Tesla, we want to translate it to the target contrast. So we want to translate the 3 Tesla to 1.5 Tesla or the other way around, just to make the images more comparable, such that we can then solve other downstream tasks. So Alicia Durer, she works in our group as well. So she took the technique that I just presented you before and used this for contrast harmonization of MR images. Here, so also the method that I presented you before works on 2D slices. And the reason why is because it's already slow in 2D and there are a lot of memory requirements. So what she did, she took a scan of the first contrast, for example, a 3 Tesla grain MR image. And then first thing, she sliced it like from top to bottom. And then she has this 3 Tesla slice. And then she trained the diffusion model to translate this 3 Tesla slice to the same slice, so with the same anatomical information, but just in the 1.5 Tesla contrast. And she does this also by concatenation. So the diffusion model starts from noise and generates a 1.5 Tesla image, but by concatenation, she adds the anatomical information that she wants. And then she can translate slice by slice, then stack it all together, and then she has the transformed MR image in the desired contrast. And this worked quite well. So on the top row, we have the transformation from 3 Tesla to 1.5 Tesla. And we see that the ground truth and the diffusion model output really look similar. And also in the other way, 1.5 Tesla to 3 Tesla provided good results. The downside of this approach is that we need paired data for training. So we need to have the same subject scanned in both scanners for our training data set. And then another approach that we can use with this method of concatenating like the conditioning image is for implant generation. And there we really run into trouble regarding memory. And that's why we switched to point cloud diffusion models. So the task here was to generate implants for skull defects. So we have 3D data by default. And then because we have 3D data, we said, okay, the skull is just a shape. So we can use point clouds. So instead of the voxel space, we have the diffusion model in the point cloud space. So now the condition that we concatenate is the skull with the defect, and we have a diffusion model that is trained to fill the defect such that in the end it looks healthy. And this is a paper by Paul Friedrichs, who also works in our group, and he will present this at MedAI next week, or yeah, in 2 weeks. So as I said, the goal is to complete a skull that has a defect, and due to memory issues and computation time restrictions, we do the whole thing in the point cloud space, and the conditioning image, such that just like the MR image as it was before, is now the skull with the defect. And so when we start, we get a CT image, and this CT image is in the voxel space. So first we have this defective skull in the voxel space, and we need to generate the point cloud using marching tubes or something like that. Then we complete this skull in the point cloud space using the diffusion model. And then we use a point cloud voxelization network to go back to the voxel space. And then just by Boolean subtraction between the defective skull and the complete skull, we can then compute the implant. And I hope, yeah, it works. So this is how the diffusion model works. So we start from a random point cloud, and then it just zooms into and places itself to fill the hole. And on the right, you can see some generated implants. So it works on the eyes, it works on the back of the head, and also in different locations and in different sizes. Good. So that was the point cloud completion task, or point cloud diffusion models for point clouds. Now the last part is the weakly supervised anomaly detection. And here we need to change the scheme a bit, because so far we always had paired data. So we had 3 Tesla to 1.5 Tesla, or we had a skull result to a complete skull, or we had the MR image and its segmentation mask. And now for weakly supervised anomaly detection, we don't have paired data sets anymore. So we cannot condition through concatenation anymore. And that's where we need to think of something new. And maybe anomaly detection, here we need to be a bit careful. So here we talk about weakly supervised anomaly detection, meaning that we use image level labels only. So we do have 2 data sets. We have a set of patients that are affected by a specific disease, and we have a set of images of a healthy control group. But we know which images belong to which class. So we know which images show a patient, we know which images show a healthy control, we just don't know where in the image the anomaly is, and that's what we are interested in. So our goal is to have image-to-image translation between the 2 sets, but these 2 sets are unpaired. And the goal is that if we have an image of a patient, and if we have such a model, we can then translate it to its healthy reconstruction, meaning that this is the image of the patient if he or she were healthy. And if we manage to do that, we can then just take the difference between input and output, and this will show the anomaly, and that's what we want. Now the trick is, so here we want to detect the pleural effusion. If we take the difference map between input and output, it's important that not the shoulder is changed, none of the bony structures are changed, and just the anomaly is changed. And this is a challenge. And here I want to present you how we solve this problem. I presented this approach at the MedAI conference last year with this paper called Diffusion Models for Medical Anomaly Detection. But again, here we talk about weakly supervised anomaly detection, so it's not unsupervised anomaly detection.
I have a question here.
Sure.
So what do you mean by the anomaly in your setting?
Anomaly in my setting is, for example, that's a good question. It's just anything that it's not healthy. So anomaly in the medical sense, for example, a tumor would be anomalous, or a pleural effusion would be anomalous, or brain shrinkage, if it's too much, would be anomalous.
And if that's the case, how do you connect the idea that you, let's say that the patient has the tumor which is showing on your left side figure before, the image behind this paper, and then you want to say that's what's the counterpart of this patient if she or he is healthy. How do you connect these two things together? I don't get that.
I'm not quite sure I understood like acoustically.
Yeah, so here, let me explain it a bit more. So you said that the left part is the image of a patient who maybe has a tumor or some disease. And then the right part is the healthy reconstruction.
Yes.
That's like if this patient is healthy, how his or her chest array will look like.
Yeah.
Okay, so how does that related to anomaly detection?
So in the to anomaly detection, so if you then take a look, maybe I need to reformulate. So the image on the left is what we get. That's the true image.
Yeah.
And the image on the right is a fake image. That's what you generate. And anomaly detection then is only if we take the difference between input and output of the model.
Okay.
And this, like anomaly detection in this sense is, it's not, is this patient healthy or not? Because that's what in our training data set, we know that. It's what area, like what anatomical structures are affected by the disease. So for example, here you see in the difference map, you see this part of the lung is red and yellow, meaning that there is something weird. And that's what we interpret as anomaly detection.
Oh, okay, I see. So anomaly in this case is that which part in the image of the patient is anomaly.
Exactly.
Okay, got it.
Okay, thank you.
I also have a question there. And can you also obtain a measure of uncertainty for this as well, like in the previous approach?
No, and I will explain you shortly afterwards why. Because, well, maybe I do it on the later slides and I come back to this question.
All right, thanks.
Thank you.
I have a question. So the healthy reconstruction that you've made, how can you be sure that it's a healthy reconstruction? If there's some error there, then the difference will not give us the anomaly, right?
That's true. So what we did to evaluate whether what we are doing is correct is, for example, we took the Bratz data set and we did this. And then in the difference map, what we wanted to get is the tumor. And we can compare this to the ground truth segmentation of the Bratz data set. And then we can compute the die-score, like whatever you want. And then you can kind of check whether this makes sense, whether we get the anomaly. But in the case of brain tumors, it's easier because it's segmentable, but there are other structures. For example, what happens if the whole brain shrinks? Then the difference map will cover the whole brain. And then it's more hard to compute the die-score to get like one score, how good we are actually.
Yeah, I get it. Okay, thank you.
Great, thanks for the questions. So I go on. So as I said, it's important to preserve identity in non-anomalous areas. For example, if you want to check whether something in the lungs is anomalous, we want to have like the shoulders and all the rest stay exactly the same. And for this, we move to denoising diffusion implicit models. And there, the trick is to remove the random component that I highlighted before. And denoising diffusion implicit models were presented in this paper, also 2021. And these are kind of a variant of the paper that I presented in the beginning, and where they just remove this random component. So what we have is xt, it's a noisy image at time step t. And because we remove the random component, this whole process gets deterministic. So we just subtract epsilon theta, that's the noise that we predict, and we get a slightly denoised xt minus 1. But because we have a deterministic denoising process, we can just add epsilon theta and go back to xt. So now we can go in circles. And back to the question before, whether we can now measure uncertainty with this. And the answer is no. And why? Because we removed the random component. So we removed the tool that we used before to generate n different predictions by this random component. So now we removed it, which is good because now we can go back and forth without losing information. But we lose also this uncertainty estimation aspect of that we had before. So now, because it's deterministic, we can start from an image and go through this iterative noise encoding by adding noise, and then just go back by iteratively removing noise, and then we end up with the same image. And so far we haven't gained anything. We just know that we add and remove noise and we don't lose information. That's great. But now we apply a trick. So, or just as I said, maybe I need to highlight this. So this going back and forth noise and getting back the same image, it's actually a big advantage compared to GANs, where it's always some sort of struggle to ensure this identity preserving mechanism. So we could have cycle GAN with the cycle consistency loss, identity preserving losses, which is kind of a pain to train. And here we get it for free. And now, as I said before, the goal is to translate an image to its healthy reconstruction. And how do we do that? So we need to add another component, and this is a classifier. So we train, as I said before, we have two data sets. We have a set of images of a healthy control group, and we have a set of patients that are affected by a specific disease. And we train a classification model, this is binary classification, as simple as it can get. And then we add gradient guidance. So we start from an input image that may show an anomaly. So this example shows a tumor. And then we go through the deterministic noising process, and then we have an image encoded in noise. And then during the denoising process, we add gradient guidance. And this is like the key point of the paper. So we just have an image at time step t, so it's a noisy image. We pass it through the diffusion model, and the diffusion model predicts us noise. This is just as we had it before. Then in addition, we pass this noisy image through the classification model, and here we can add a desired class y, and the desired class for us, it's always the healthy class. And then we compute the gradient of this classification model with respect to the input pixels of xt for this desired class y. So this gradient map indicates the pixels that contribute to the healthy class. And then we update the predicted noise pattern with this gradient map. So this is just an addition. And we then take this updated version of epsilon to predict xt minus 1, which is slightly less noisy and slightly more healthy. And we do this during every step of the denoising process. And in the end, then guide the image generation towards the healthy class. And then in the end, you can take the difference between input and output, and this gives our anomaly map. So yeah.
I had a quick question here, actually. So in this case, if you're able to add the gradients from the classification model to your diffusion model, is there like a lot of architectural similarity between the diffusion model and your classification model, or is it like some variant of each other?
No, actually, it could be completely different. The only thing, so this update, this is the addition of epsilon theta and the gradient, which means that they need to be of the same dimension. But the model architecture Could be anything. But what we did actually is, so the diffusion model, and for the classification model, I just took the encoder of this unit as architecture. And the reason there is because in the diffusion model, we add the time information. So we tell the model in what time step we are. And I do the same for the classification model. So I let the model know what is the time step t. And that's why it was just easiest to copy paste the encoder.
I see. And you've already trained the classification model separately, or is it also getting trained in the same process?
No, it's completely separate. They are completely independent.
Okay, thank you.
Thank you.
I'm a little confused because I know you could also do like guidance generation process for the diffusion model with stochasticity. What's the main point of using deterministic here?
The main point is that we want to have, like, if you consider the input image, we want to have the same in healthy. And the trick of the deterministic is this encoding, decoding, which ensures, like, if you go one slide back, oops, sorry. Here, so the trick of deterministic is that if we don't add gradient guidance, you get back the exact same image. So it's the identity preserving part that needs the deterministic process.
Okay, thank you.
Thank you. Okay, yeah, here are just some results in the Bratz data set. So in the top row, there's a slice of the original input data set that contains a tumor. So here is the ground truth segmentation. And in the bottom row is the output of our model. So that's the healthy reconstruction. And if we take the difference between input and output, that is shown in blue and yellow here, we see that our difference map quite accurately highlights the tumor. And then we did the same on the Checkspread data set. So the first row is the input. The second row is the healthy reconstruction. And we again see, like here we have some mistakes in lung areas that maybe should not have been changed. But nevertheless, it tries to make like the diaphragm like more or less the same height in cases of pleural effusions. So here the classification task was between healthy and pleural effusion.
I had a quick question slash comment about this. So it seems like the accuracy of the classification model, or rather how well the gradients of like if you do a saliency on the classification model, how well that is able to capture the anomaly kind of drives this whole process. How do you ensure that that is good enough for your, like if that's a bad classification model or it's not very good, you're going to be subject to the same kind of problems?
Yes, that's what I would expect. So if the classification model is bad, this whole diffusion guidance would also be bad. It's maybe a bit different in the diffusion case. So it's not like in the saliency map, you have one step. It's just like from output, like from the score back to the image. But here we have 1,000 steps. And so here the diffusion model and the classification model, they play together somehow. And in every step, there is a response to that. So it has some time to save itself, I'd say.
I see. So is it fair to kind of say the classification model provides like a starting point or a prior to your this thing, and then your diffusion process essentially is refining the whole process to get a better identification of the anomaly?
Yeah. Okay. And it's, as I said, it's not just one shot. It's this iterative 1,000 steps.
That makes sense.
Out of trouble.
And also, just one. Sorry. Do we have time for another question? I was wondering. So basically, with this approach, you need to define the classes that you're interested in ahead of time. And also, it seems like you're mainly going for one class at a time. So in this example that you showed with the chest X-rays, only going for pleural effusion. What happens if you were to go for multiple classes in your anomaly detection?
Yes, so it's possible. We also tried it. And the only thing that you'd need to change is the training of your classifier, actually. So I think in one of the diffusion papers, they trained it on ImageNet with 1,000 classes. And it just works basically the same. You just need to specify the class you want to generate in the end.
Okay, that makes sense. Thanks.
You're welcome. So I think you're slowly running out of time, so I skipped those 2 slides. It's just the analysis that's also in the paper. And here I wanted to highlight that also in MonAI generative, there's also a tutorial with this DDIM, so the deterministic noise encoding, and the decoding with the gradient guidance. And then, as I said in the beginning, so this approach works well for weakly supervised anomaly detection. So if we have the image level labels, and I introduced you the gradient guidance, you could do the same using classifier or gradient-free guidance. And so the noise encoding and decoding using the deterministic process stays exactly the same. It's just a slightly different way of training. And this was presented here in this paper called What is Healthy. So we followed a similar idea, but he just did it not using the gradient, but a condition in the latent space. And then for unsupervised anomaly detection, so training only on healthy subjects, was also explored in this paper by Wolleb. And there he used latent diffusion models and trained only on healthy subjects and tried to detect brain lesions. And also one thing to note, or one limitation, is that the approach I presented was implemented in 2D and it worked well there. However, we are dealing with MR images in 3D, and this will need to be evaluated. So Florentin is also in our group, and he wrote this paper called Diffusion Models for Memory Efficient Processing of 3D Medical Images, but we haven't applied it to the anomaly task yet. This paper is for the segmentation task. It worked well, but there's still some open work to do. And I just half a second, this approach can very easily be extended to other tasks, because I said that we take the gradient of a classification model, but this is not restricted to classification models. So we could also consider regression models or segmentation models and just take the gradient with respect to those models for image-to-image translation. So here, for example, I trained an age regression model, and then I took the gradient to manipulate the age of the person in the image. So I could make them older or younger using gradient guidance, just as I explained it before. So these are the 4 topics that I covered today. I think in conclusion, we can say that diffusion models show a very stable training because we have one network, which is a unit architecture with one loss function, which is an MSE loss, so it's quite simple. And downside is that the sampling times are long because we need to go through this iterative process. And people looked into this and they came up with solutions. One was proposed here in this paper called Elucidating the Science Base of Diffusion-Based Generative Models, and there are also other ideas around. And one step would or could be to switch to latent diffusion models, which are diffusion models in the latent space. And there we could save some memory and also speed up the whole process. And this is the latent diffusion model paper, which is worth checking out. And then there are many other applications that I didn't talk about today. Some of them are here in the survey by Dorit Merhoff, and yeah, or if you Google, you find tons of papers. Now I thank you, and if there are any questions, I'm happy to answer if you still have time.
Yeah, thanks so much, Julia. This was a great talk, very comprehensive, starting from diffusion models and all the other use cases that you covered. So thank you very much. I guess we're almost at time, but if you still have like 5 more minutes, maybe we can just let the audience ask any last minute questions that they have. Oh, I guess before we actually start the questions, let us give our speaker a round of virtual applause. So thanks again, Julia, for the wonderful talk. I saw a couple of questions in the chat. So maybe Sabine, do you want to ask your question?
Yeah, I was just asking whether you've compared your uncertainty maps with the ones generated by ensemble of NN unit segmentation.
Yes, we have, so the results can be found in the paper actually. So what we did, we plotted them, so we compared it against the epistemic and the aleatoric uncertainties that can be done with the normal unit by drop out layers actually. So just to wait, I think you refer to this, just adding like masking out random model parameters to check the uncertainty within the model.
Yeah, so basically you're adding kind of variant or uncertainty or like different noise levels, right? And then calculating uncertainty, using that to calculate the uncertainty, right? In your case. But if there's a deterministic model and you use an ensemble of those deterministic models and then calculate the variance, the uncertainty maps generated using that ensemble of deterministic networks, is that very different from what you get, or?
No, it's not very different. I think, so when we compared the two maps, so we, in the paper, you can see them just right next to each other. And you see the similar regions in the images outlined, which makes sense because that's maybe the regions in the image where the information just is not clear. I think when we compare the ways how we got to these two uncertainty maps, although the results are very similar, I think the methods are like different because if we compare, like do the deterministic unit with the dropout layers, like you randomly mask out model parameters. So you take away some of the model's power to check how well it still performs. Whereas on our approach, the model always is in its full size. So I don't steal anything from the model. It's just by this random component that is in the sampling process. And we found it quite interesting that two so different approaches can be also compared, like in the end on the images.
Right. Okay. Thank you.
Do we have any other questions from the audience? Okay, I guess if not, thanks again for the wonderful talk, and we'll put up this video on our YouTube channel sometime later today or tomorrow, and then hopefully if you have more questions, you can always reach out to Julia, or you can reach out to us and we can put you in touch with her. So thanks again, everyone, for staying with us on this talk, and then we'll see you all next week.
Bye.
Awesome.